Hello. In this video, let me show you how to solve 2022 AMC 12B problem 17. So this problem asks us to find out the 4x4 matrices such that every entry is 0 or 1. And we should have the property that the number of ones in 4 rows are 1, 2, 3, 4 in some order, and the number of ones in the 4 columns are also 1, 2, 3, 4 in some order. So how many such matrices do we have? You can do, like, for instance, casework analysis or whatever, but that would not be a very efficient approach to solve the problem. So I want to actually, before starting counting, I want to first explore some structural properties of such matrix. Actually, I observed the following facts. So first, if you swap any 2 rows, say, for example, you swap row 1 and row 3, then you observe that. So suppose that the matrix before you swap satisfies all the conditions required by this problem. So let me call the matrix satisfying all these conditions as a feasible matrix, okay? So I'm saying the following thing. For a given feasible matrix, if you swap any 2 rows, say row 1 and row 3, then it's still feasible. So it can be easily verified, right? And similarly, for a feasible matrix, if you interchange any 2 columns, say, for example, column 2 and column 3, the new matrix is still feasible, right? So given this observation, it tells us the following thing. So every feasible matrix could be obtained through such swapping operations, maybe one swapping operation or some combinations of swapping operations, that it could be obtained by starting from a benchmark matrix such that for this benchmark matrix, the number of ones in row I is equal to I. The number of ones in column I is also equal, in column J is also equal to J, which means that, so in order to get a feasible matrix, so we can always start from the 1 such that in row 1, we have 1 1. In row 2, there are 2 ones. Row 3, 3 ones. Row 4, 4 ones. And in column 1, single 1. Column 2, 2 ones. Column 3, 3 ones. Column 4, 4 ones. So we call such a matrix a benchmark matrix. Is it clear? All right. So the next problem is, how many such benchmark matrices do we have? So let's construct such benchmark matrices. First, recall that row 4 should have 4 4s. So the bottom row should be with all ones. Or should be 4 ones, not 4 4s, my bad. And second, because the rightmost column should have 4 ones. So every entry on the right column is 1. Okay. And then recall that the number of ones on the first row should be 1. We already have 1 on the first row, so the other 3 entries are all 0. And recall that the first column should have unique 1. We already have 1 at the bottom, so the other entries must be 0. Okay? And then let's look at row 3. So this row should have 3 ones. We have 2 entries whose values have not been assigned yet. In order to get 3 ones, these 2 must be equal to 1. And then let's look at column 3. Again, this column should have 3 ones. Therefore, the leftover entry should be 1. And then let's go to row 2. So this row should have 2 ones. So the leftover number must be equal to 0. So this construction tells us that such benchmark matrix is unique. Is it clear? Okay. So next, we'll use this uniqueness fact and the swapping property to count the total number of feasible matrices. So the two properties above tell us that, so for any feasible matrix, it could be constructed by starting from this unique benchmark matrix. And starting from here, so we'll do a bunch of the swapping operations between between different pairs of two rows. And we could do such swapping operations on the columns. And after doing some combinations of such operations, so we could eventually get to a feasible matrix, right? Or in other words, think about it. If we do the several combinations of the swapping operations for the rows, so it is equivalent to coming up with the permutation of these 4 rows. And similarly, if we do some swapping operations of columns by putting them together, it is equivalent to coming up with the permutation of those columns, right? So now we know how to construct the feasible matrix starting from this benchmark one. So we could do it in 2 steps. In the first step, we come up with the permutation of the 4 rows. The number of ways is 4 factorial. In the second step, we develop a permutation of the 4 columns. The number of such permutations is also equal to 4 factorial. So the total number of feasible matrices is equal to the product of these 2 numbers. And 4 factorial is 24. 24 times 24 is equal to 576.